Hello and welcome back. Today I have another LCR meter, and this time it is from Zoyi from Zotek Tools, and it is the ZT-DQ01, and I also have the ZT-DQ02. And the little difference is it also has a battery resistant meter in the top. I already did some reviews about LCR meters, and I think a few months back I did one with the DER 5000 and with the East tester. So why do I do this again now? Well, I think these meters are interesting because of its price point. It could be a very nice starter if it is good enough, because I don't expect it to be as good as the DER 5000 and not as good as the East tester. I have here the 432, and in the test they were quite good. But don't forget, the DER 5000 is almost 3 times the price of the Zoyi, and the East tester twice times the Zoyi. So what do you get for that money? Well, at the first glance they look very similar. This is the DQ1 only LCR, and this one also has the battery meter, so there is of course a slight difference. If you think, well, they look very familiar anyway, well, that could be because of their oscilloscope. This is the 702 oscilloscope, looks very similar, and even I have here the 2-channel, the 703, only the display is slightly bigger, but we can see the casings are very similar, I think even on the back. So that will probably save them some cost with the production, of course, if you can reuse certain things, and that is how they can keep the price low. Then let's look at the difference of these two. That is just the top connector here for the battery resistance meter. So what comes in the box? Well, it is sort of a white label. I don't see a real brand, so this will probably be rebranded as well by others. It comes in a nice etui here. Let me take this out. I ordered one with the Kelvin clips, and they look actually pretty nice. It are those security plugs. Nothing wrong with that. By default it comes with these probes. It is not silicone, but it is still soft plastic. And all nice. Ooh, pointy, not bad at all. USB cable to charge, but it can also do data export, firmware update, and they do maintain their firmware update still also for the oscilloscopes, and a little isolator for the clips here, which I will explain later. DQ02, same box, also no type numbers on it. But I did have here, it says here LCR meter with battery test. Well, that is about correct. Same, nice etui. And this one you can also order with the Kelvin clips, but these are the Kelvins for the battery tester. So it probably has that battery connector in the top right here. Yes. And well, looks sort of the same as the other Kelvins. Same type of probes. Also USB and the same isolator, so quite complete. These are the standard probe to measure for the 2-wire standard. It comes with both. This you can order as an extra, the Kelvins, and this one only comes with the battery tester. So as I said, it's very flexible, but it is not a silicone. This looks very sharp, and I like this detail that it is in a little angle, so it is not, look at that. I like that, instead of it sticking out all the way to the top. And it is a tight fit. You can even hear it. Yeah, good. So this battery tester Kelvins, it looks quite good. There is good power on the spring. I'm not sure what I do with shielding. If they do shielding, it doesn't seem to be. If I look at this, or these are two little coaxes. This, for me, it's a little bit of a weird plug, but maybe it is just a standard plug for battery testers. I'm not that into battery testers, to be honest. And well, we have the Kelvins. They look very similar. They probably are, and only in the end they made a little change here by changing this plug into just standard bananas. Same, good strength. And how is the fit with this? Yeah, also good fit. There is also a possibility to use these Kelvin clips, and the upside with that is that you have a card connector. So you have extra shielding on your connector. So you can use these. These are also universal. And as you can see here, it is guard. So if you're measuring with high, it's a good tight fit. I like that, because in some LCR meters, it just almost falls out and you need to move it left to right to lock it, because it kind of locks here. But this is a real tight fit. That's very nice. I was saying, oh yeah, the guard. And you have some extra shielding if you're measuring on higher frequencies, because it goes up to 100 kilohertz, which is quite a bit. Why we have this isolator? Well, if we look inside the connector, and I hope we can see that the high pot and the high current, low pot and the low current, are both connected to each other. So that means they actually short this one and they short this one. So when you use a 2-wire, it doesn't matter too much if you use this hole or this hole or this hole and this hole. But usually I think you would use the current because it is shorted here through this connector. But when you are measuring 4-wire, you actually want to use 2 on both, and the short you don't want to be here, but you want to short here on the device that you're about to test. It's close to the point here. So that means this short you need to break, and you do this by adding this isolator, and that's the use of it. It is indeed sort of a solution, but then you wonder why you make this 4-wire, because you don't see that on others. You see it like this. You just have a 2-wire here, and then you have an extra hole for the guard, for your shielding. And if you want to use 4-wire, you just use this that I showed you before. They could have chosen that. They don't do that. Yeah, okay, it's a choice. Let's fire it up, see if the menus are very different. They start, the O2 is a lot faster. That is funny, because it is more hardware, you would think. So if they do sort of a self-check or a self-calibrated startup, why is it faster? Oh, by the way, the display is very clear. It's all big digits. I like it. Even with my eyes I can see properly. But going into the menu, probably long push. Yeah. This is firmware 108. That is, by the way, interesting, because on the website you can only find 107, and that's the latest. So apparently it's not the latest. And this one, yeah, that is what I would expect. So maybe the firmware 107 is faster than the 108. I don't know. So let's first upgrade them for both to the same version. Let's try that again, both running 108. Yeah, it seems really faster, the DQ02. Then maybe there is we need to check inside if there is a faster processor, or they did more than just adding that plug in the top. I read in the manual that you don't need to calibrate it, because it comes calibrated out of the factory, but we did do a firmware update, so maybe we need to do an open-close calibration just to be sure, especially when we're going to use the 4-wire. But I went through the settings here. We can set the frequency levels. I will always start with 1K. It's just as a default. And 0.6 volt. No bias, because we do not do electrolytics. Sometimes you want a little bias. So you add a little bit DC, just to raise it a little bit. Here we can set the equivalent, serial, parallel, or just auto. It depends if you have small caps or big caps. Sometimes it's better to do serial, the other time it's parallel. And for inductance, the other way around. We have here the resistance, capacitors, inductance, impedance. And here we have electrolytics also for tantalums. And this is then the battery options that the other doesn't have, but I keep it in auto. Let's do some simple 2-wire testing. I didn't calibrate both of them, so just factory calibration. I have the DMM check plus. The values are known here. They were measured with 0.05 accuracy on the BK891. I also did it myself on my 0.05 LCR meter. So the temperature might have changed a bit, but these are automotive resistors and capacitors, so they are kind of used to being changed in temperature. So that was a good pick from the DMM check plus. So just let's have a look. If we just get, will it detect that it's a resistor in the first place, and what will the value be? Look at that, this is 100k. Can I just hold this? Yeah. Well, we can see there is a slight difference between the both of them. And maybe that is calibration. I see here the 100 ohms is measured as 100.033, and on my meter it was 0.35, and we see here 0.3. So this one looks best now. So after calibration, let's see again. We do this 100k, and this one is again a little bit low, and this jumps a little bit, but it is around 63, 64. This value, it increased a little bit because he said 100.03, and it was actually spot on, and now it is a little bit higher. But this value somehow doesn't seem to stabilize, and that is weird. Okay, I think that was just a contact issue. This one is again around 24. This one jumps a little bit more somehow. Seems to be a little bit restless. This is now on 100 ohms, and I selected now the dissipation because maybe that is better to measure on a simple resistor. 1k also. This is exactly 1k. This should be a 1. This one is again also fractional high, and here it's again around 800, where it is here around 1000. I do a little electrolytic. I do not put any bias. I just have the same 1 kilohertz, 0.6 volts. And look at how fast the detection is. Puff, it's immediately there. It doesn't need to, and it switched over. And look, they agree a lot more here. What else we can see? Q factor close. Here the Q is a little bit higher. X, probably cannot do X here. Well, they do agree. Phase, quite similar. And by the way, how much should it have been? 1 microfarad is 10566. 105, well, close enough, I would say. Now let's go to very small. This is 1 nano, and that should be 0.97. 0.97, indeed it is. 0.97. Let's do some coils. I have here 1 microhenry. Let's see if it will detect 1 microhenry. It doesn't know what to do. It thinks it's a resistor. Well, that is quite normal. Let's switch that over to coils. It thinks it is 0.9. Where have all my digits gone, by the way? Well, let's see what the other says. It is 80,000 counts, but I see now not too many counts. Look at that. Resistance thinks it's the same. And 0. This is actually a little bit low, but what if we increase the frequency? Do we get a better reading then? We are now on 1 milliari, and we have now our digits back. It should be around 104.224, and that we have close to 104, so that is not bad at all. We look at the defactor, that is also quite similar, that they both agree on. Oh, I didn't think about it, but it's actually great. I use the hold function here, but it works even in the other screens. Look at this, I'm switching over, and it even recorded that in the same hold function, because this one is not connected, and I put it on hold, and I was actually expecting that it was only saving the current screen, but it is saving all the screens. So if I switch now over again to X, I'm going to say here, look at that, it stored that screen. This is live, and this is my hold function. I'm a little bit amazed about that. That is pretty neat. Look at that, all agrees here. Wow, that is a cool hold function. Okay, I also calibrated the standard Kelvins that you can order as an option with the isolator. But the user interface you need to get used to, because there is not always the same button to confirm and to exit. Because if I push long for the menu, for the calibrate, instead of pushing, this is usually the enter button, but now I need to push the arrow to get into the menu. But if I want to accept here, I need to push the middle one, and if I want to exit, I need to push this one. So sometimes the enter button is confusing which one you need to use, but you probably will get used to that at some point. Yeah, now I wanted to go back to the menu, but of course it doesn't work because I'm in this menu, and then I need to put this button. Yeah, I measured the difference between using these optional Kelvins or these special shielded Kelvins, and the difference was actually quite small. I did both with the same meter. I used the DQ02, and here I have the shielded Kelvins, and here I have the Kelvin 4-wire. And when we look at the resistance, it is near the same. The only thing I found the difference was here with the coils, with 1 microhenry, that here it is 0.9 and here it is 1.2, but the rest is 9.5, 9.4, 10437, 10437, 10302, 10381. So I think you can use the original cables there. So looking at the results, it probably doesn't make sense to buy something like this for this meter, because this meter was around 60 euros. This is 30 euros, and the difference with the optional Kelvins, these are actually good. And sometimes they even gave a more stable reading than the special clamps, because the contacts seem to be a problem sometimes. So if you're thinking about this meter, I would go for these Kelvins and not the special ones. Then quickly, let's have a look at the battery meter option. So the battery meter option is only available in the DQ02, and it is just if we cycle through the menu. It is just the last option before it goes back, and then you have your voltage readout right there. Here we have the resistance, and here we can set some values. I set it now to 13.5 as a high and the voltage low as 11, because I'm going to measure 12 volt battery, and my resistance probably between 100 milliohms and 1 milliohms. So that is the levels I set it to. These levels do nothing with the measurement, but it will change what you see in the display. Now we are outside the limits that we set, so we see the readout is red for the resistance also. So maybe I want to change this to 50 milliohms and 1 milliohm, but I will just leave it as it is. Let's get the battery. So we have two 12 volt batteries here. One is good, one is bad. So let's have a look. Well, we set the levels between 13.5 and 11. So that is one value, but that is more if it's full or if it's empty. You see it takes a little bit. It says it's 12.639 volts, so that is within the limits. So we see the values are in white digits, and also the resistance is between the 100 and the 1 milliohms, so that is also. So let's try the other battery. So not only is it empty, so we see here 797, but we also see it is 150 ohms, which is of course way too much. So it's not only empty, but it is also broken. Well, I know it is broken, and we can see that the digits are now also red. Well, I can't really compare it to another proper meter, but I have another cheapo that more or less does the same, but it only does battery measurement. So let's try this again with the good one. Bleep, it said, so the measuring is finished. We stop the measurement, and let's see what this one thinks it is. Look at that. If we look at the resistance, it is very close, and the voltage can change a little bit. It depends also on the load that the measuring device puts on the battery, if it is the same or not. But we see also it is variating fractional, but I agree. So the broken battery, I hope it doesn't drain so fast that the value doesn't align anymore, but let's see. Now we have a different resistance. Now it's suddenly 170 instead of 150 that we had before, but I think it stabilized. Yeah, what will a broken battery do? I don't know. Stop. Let's get the other meter. Does it agree? Well, look at that. It does agree. 8.6 also, and the resistance 172. Well, let's put it to the test, and I will set it here to that it needs to be within 30, and then this digit is probably going to be red. Yes, look at that, it's indeed the case. So we have here a white digit because it is within the 13.5 and the 11 volts, but I set the resistance between 30 and 1, and it is not. So it says it's not good. So what if I try to change this again? Let's say 32. So you can do pretty, and here it is. It's immediately live also. So you can do a very good test if you know what the values should be, and you see immediately by red and white. So opening was quite smooth. There are 4 screws, and after that it was stuck. But of course I have my nice tool here. It almost looks like dental tools, but then you don't damage the device. I really needed to pry it open, but here in the middle are 2 hooks that is still keeping it tight. Well, it has a 2000 milliamps in both, and we already see slight differences. Let's have a closer look. Well, most of it looks the same, but we see already there is an extra PCB here. There are here 2 big caps that is not here, but also here we have some ICs, some little diodes, I think. Maybe it's to generate AC here. And a lot of components here also. It really added. This whole area is populated here, and here it is not. Okay, it's now upside down. Well, it doesn't seem that the main processor here is different, so why it starts up faster? Maybe here it is looking for this part that is not there, and then it takes half a second extra. But here we see this is all unpopulated. And here we see a lot of components extra, and that is the main difference. Well, first I was thinking, why would you put a battery meter inside of an LCR meter? Because it is kind of weird now. One is just for big batteries and the other one is for fine electronics. But then I was thinking, it does make sense. So I have here a standard DMM multimeter. I am measuring the ohms. It's almost 100 ohm. I have 100 ohms here. But how does that work? Now, the meter just put, let's say, 1 milliamp through this resistor, and then it measures the voltage over this resistor, and it's calculated, and then it will show as the resistance. But what will happen if you add a source, like you're trying to measure a battery? So when I do this, it goes to 0 ohms, but if I put it the other way around, it will say overflows endless. So there is a problem. We need to take the DC component out when we want to try to measure the resistance of a battery. So we use a DC block. What is a DC block? It is actually just a capacitor in series. But then how we measure the resistance? Well, instead of using DC current, they probably use AC current. And that means we need a little generator inside of the device. But it is already an LCR meter, so it does have its own generator already. Only thing we need to do is amplify it a little bit. And that is probably what we saw. We saw these big capacitors, that could be the DC block, and all these little components are probably op amps to amplify the AC current. Well, I'm not 100% sure that is the way they do it, but it seems to make sense. So how does that work? Well, we have a USB connector here. That is where you charge, but you can also connect it to the computer, and you can do data export with the SCPI, but you can also do firmware update. We need to hold this button in the top here, push here, and it says USB boot. Then you connect it to the computer. Okay, I have the cable here. I will plug that into the computer, and it should create a drive now. And it did. It is F. So let's open that one. F. Okay. Bin to here txt. So we probably need to put the bin there. I already opened that folder. I've stored here all my firmware. Well, I couldn't find on the official website 108, but I did find it on the EEV blog, and I need a DQ02. So let's do this one. Copy. I paste it in, and what will we see on the device? That was super fast. Let's see. Yeah, we have now 108. When you switch on the device first and then you plug in the USB connector, it will create a COM5 serial port, virtual port, and with this you should be able to connect with the SCPI. So I have a few devices here. It's not USB, it's COM15 I have here. So that works with the Keysight Connection Expert, but you can, I think, also just use the from National Instrument Max. So I think for the price it is actually quite good. And then you need to go for the standard 4-wire option. I think it was between 5 and 10 euros or dollars. So then you have something around 70 euros instead of 120 or close to 200. And it seemed to be quite accurate on the primary values. If the secondary values, like the reactions and the dissipation, if that is any good, I didn't test that far, but I got the most stable readings using also again the 4-wire Kelvin clips from the option. So pretty nice for starters, I think. Thank you for watching, and I hope to see you next time.